Now I'd like to run you through a couple of examples. The first example we're going to look at is an application of the binomial probability distribution, and the second for the hypergeometric probability distribution. So remember, the binomial probability distribution, given by this function here, which we've just gone over, it gives the probability of r successes out of n tries. And the important point here is the probability of a single success is little p, and that's constant throughout the experiment or throughout the series of trials. Little p does not change. So let's look at an example, and I have one set up on MATLAB, and this script here is available on our website for you to use as you would like. You can experiment it. But the first example I have set up is an example of what Davis refers to as the gambler's ruin. So we're prospecting for oil, and we have to drill a number of holes, and we want to estimate the probability of complete failure. I need to change these notes. Let's see. Okay, complete failure. So probability of 0 successes. So say we're given some data where we know from prior experience that the probability of any one hole coming up successful is 10%, 0.1. Little p is equal to 0.1. And we're testing what the probability is for r equals 0 successes, and we're going to vary the number of holes we drill. We're going to look at a case in which we drill 1 hole all the way up to 20 holes. And this is our equation for big P, the probability. Okay, and I've just typed that in. And one thing I'd like you to note is, please, since n is a vector, it's an array, it's crucial that we have dot slash for divided by, or dot star for multiplication. When I first wrote this, I failed to put this dot here, and I got an answer surprisingly, but it was wrong. So make sure that dot is there. So let's go ahead and run this. Okay, so, and I'm going to plot a bar plot of n versus p. Okay, so we see here that if we just were to drill 1 hole, the probability of failure is 90%. I mean, maybe that's maybe that's somewhat obvious, right? If the probability of success is 10%, the probability of failure for 1 hole is 90%. And the probability of failure decreases with the number of holes that we try. And it's important to see with this 10% success rate, in order to get over less than a 50% chance of failure, we need to drill something like 7 holes, 7 or more holes. So this is a way of assessing your risk of coming up empty-handed. If you want to make sure you don't come up empty-handed, this tells you roughly how many holes you're going to need to drill. Now let's play with the parameters a little bit. And let's evaluate the probability of r and only r successes as a function of the number of holes drilled. And so here we have p is still 10%. And in this case, let's look at r equals 1. So we're going to look at the probability of 1 success, and we're going to vary the number of holes drilled. And, oh, I can't do that actually. Well, yeah, sure, okay. So let's run through this script again. And, okay. So here we see the probability of exactly 1 discovery and versus the number of holes. And so again, with 1 hole we get a probability of 1 discovery of 0.1, but that probability goes up with the number of holes that we drill, and it looks like it reaches a peak, a maximum probability close to 0.4. So y beyond 0.4, does the probability of drilling exactly one hole go down? You would think that, well, the more number of holes we drill, the more likely we are to succeed. So why is that? And if you want, you can pause the video and think about it for a little while before I tell you the answer. But the reason it starts going down is this is the probability of finding one and only one discovery. Okay? Beyond about 10 holes drilled, there's an increasing likelihood that we would find greater than one holes. Okay? So the probability of finding only one actually goes down after about 10 holes. Okay? Does that make sense? I hope that's clear. Okay. Let's look at a situation where r equals 2. Okay. So when r equals 2, okay, the probability of 2 and exactly 2 holes discovered, okay, is low with only 2 holes. But as we increase the number of holes drilled, the probability of finding 2 starts to increase. And you can imagine if I extended this further to the right, we would start seeing this probability go down again. Again, because as we drill more and more holes, we're starting to be more likely to find 2 or 3 or 4 holes. But whereas this only shows the probability of finding exactly 2 successful holes. Okay, so that was some examples of the binomial probability distribution. And I should note, this is a discrete probability distribution, right? So the only possible values, we could plot probability. In this case, we plotted it versus n for a given r, or we could plot it for a fixed n varying r. But these numbers are discrete. So the probability distribution has values at discrete numbers. Okay, this is an example of a discrete probability distribution. Okay, so now let's look at the hypergeometric probability distribution. And as you recall, this gives the probability of r successes out of n tries or n samples, but in which the probability, little p, changes with successive samples. And that would occur, for example, if the population size from which we're sampling is finite. So here the population size is big N, and among those n total objects in our population, there exists a total of s successes. I'll go ahead and save this. All right. So here we have another MATLAB script. And here, okay, so let's look at a simple example. So we're looking at the probability of drawing aces in a full deck of cards. Okay, so we know that a deck of cards has 52 cards. So big N is 52. And if it's a full deck, then of course we have 4 aces in the deck. So let's say we draw one card, so n equals 1, and we want to find the probability of, I should have made this x is little r. I could do that. Why not? I better not. Just pretend this little x is little r. I'll go ahead and fix this before I post it. But so we're going to look at the probability of finding one ace in a deck by drawing one card. And we've actually done that problem before. But if we do that, get rid of my figure here. I'm not going to show any figures. I'll run that. And oops, the probability is 0.77. Okay, and that's the same as 4/52. And you should work out on paper why these factors give the intuitive answer of 4/52. Okay, and we went through that in one of the previous lectures. So let's look at a situation. If we draw, let's say we're playing poker, and we're dealt 5 cards. What's the probability of getting an ace? So if we run that, well, we get about a 30% probability of getting an ace. Maybe that makes sense with your experience. You know, roughly 1 in 3 hands you get a single ace. Okay, and we can play with these numbers. You know, what's the probability of getting 2 aces out of being dealt 5 cards? And the answer is 0.4. 1 in 25 hands we're going to get 2 aces. And of course the probability goes down quite a bit as we increase the number of aces. With 3 aces it goes down to less than about 0.002, and with all 4 aces it has a very low probability. Okay, 4 of a kind with aces you're going to have to play a lot of poker to get that hand dealt to you the very first time. Okay, so those are 2 examples, and the next video will run you through one more example of conditional probability.